Good morning. I thought we'd try something a bit different this morning with me explaining some of the work that we've been doing, and I wanted to start by looking at the reaction profiles. So last lesson you were looking and seeing that we could have two different types of profile to show you endothermic and exothermic reactions, and I just wanted to remind you about this activation energy. So if you look at both of the reaction profiles, you'll see that they've got a hump in the middle of it. And that hump tells us the activation energy, the minimum amount of energy needed before colliding particles of reactants have sufficient energy to cause a reaction. Before that point, they'll just bounce off each other. There'll be no reaction happening. So knowing the activation energy of all the different reactions is really important, and the graph helps us work that out. Chemists are able to work out exactly how much activation energy is needed for any particular reaction. So in the example on the screen, we've got magnesium reacting with water to make magnesium hydroxide and hydrogen gas. Chemists have worked out and measured that you'd need 950 kilojoules per mole to convert into products. Any energy less than that and it wouldn't happen, nothing would go. Have a look at those units. Kilojoules, so thousands of joules per mole. So remember that mole, that quantity, that counting unit that we learnt about earlier on in the year. It's all linking back together. Now we've reminded ourselves about activation energies and those reaction profiles, we're going to go back to thinking about the reactions, the endothermic being bond breaking and exothermic being bond making. So every type of bond that there is has a different amount of energy needed to make it or break it. The good news is you don't need to measure that, you get given all of that information, and there are lots of tables and databases that scientists can use to find that out. So in this example we're looking at a hydrogen-hydrogen single bond, and that has a bond energy of 436 kilojoules per mole. So if you're making that bond, remember making is exothermic, that means 436 kilojoules per mole of energy is released. And if you're breaking that bond, so an endothermic reaction, 436 kilojoules per mole of energy gets absorbed. So here's an example of a data table that you might get given with bond energies, and you can use those to calculate the total energy of a reaction. And that would be the energy in or the energy out. And that would be the difference between the energy that you need to put in to make the bonds and the energy that gets given out where those bonds are broken. Now here's an opportunity for you to actually get involved. Hopefully you've been making notes all the way through. But I'd like you to have a go at writing me a balanced equation for the reaction of hydrogen with oxygen to produce water. Underneath that, I want you to draw diagrams of the right number of molecules so that you've got the equation, the symbol equation, and then a diagram so you can count those bonds that are available. How did it go? Did yours look something like this? If not, amend it. Use that red pen. Mr. Ingham Hill still will know if you're not using red pen, and make sure that you've got the correct formula and the correct diagram beneath it. So now here are the bond energies that we need to look at. We can know that it's just these bond energies between two hydrogens, two oxygens, and an oxygen and a hydrogen. They're the only elements that are involved in our reaction. This is why having a diagram of what's going on is really important, because you can now see which bonds need breaking and which bonds need making. So have a go at writing down which bonds are broken in this reaction and which bonds are made. Remember to use the terms that are on the side, so how many HH bonds are broken or made, and so on. So looking at our diagrams, I can see that I need to break 2 HH bonds and 1 oxygen double bond, and I need to make 4 OH bonds. Looking at my bond energies, I then know that I need to add 2 lots of HH, so 436, add 436, add an O double bond, so that's add 498, and that will give me the total energy taken in that reaction. If you add those three together, you work out that you need 1,370 kilojoules per mole to break those bonds. You then need to work out how much energy is needed to make those bonds. So having a look at the reactant side, you've already worked out what bonds need to be made, so you can start looking at how much energy is needed to make them. So as we're all making the same type of bond, we're making 4 lots of OH, it's 4 lots of 464. That means that 1,856 kilojoule per mole of energy is released when this reaction happens. So we've now got the energy taken in and the energy released, and you can see that those energies are different. So we can work out the difference. So the difference is just the difference between the energy taken in and the energy released. Work that value out now. So you should have got a difference of minus 486 kilojoules per mole. That tells you it's an exothermic reaction. Be really careful around that, because some people's brains think negative means something different. But if it's a negative difference, it's an exothermic reaction. If it's positive, it's endothermic. Have a look at the graphs that we looked at the very beginning of the lesson, because that helps you see whether it's positive and negative as well. Now you've had a worked example talked through with you, it's up to you what you do next. If you haven't made notes as we've gone through, I would strongly advise you to make some notes so that you've got an example to follow. If you have made notes and you're happy, then you can have a look at some of the other examples in the textbook page. Either way, we're going to spend the rest of this lesson and next lesson becoming really confident on working out bond energies.